everyone. Hello, hello. I just thought a bit of an upbeat music for our last lecture of content, which is so exciting. So week 10 is going to be our lovely revision week. This is the last time I'll be cramming things down your throats and making you be like, yay, linked lists, or yay, whatever we're going to do today. I'm going to do multi-file projects again, because obviously I kind of gave you the speed, 11-minute rundown, I think, after when Tammy and I were having a chat after the lecture. She was like, wow, that was the fastest I've ever seen anyone do linked lists in. And I'm pretty sure no one understood anything I said. So don't worry, it's happening. We're going to do it again. Not a problem. I hope everyone had a good weekend. I hope everyone is doing well with the assignment. Please check my announcement. It's got a lot of details about the help sessions and things like that. I also today decided to do a poll for what should we do next week. What exciting things will we revise? So on Tuesday, our whole lecture, most of it, 1 hour of it at least, will be talking about the exam. I'm going to give you examples of questions that you're going to get. We're going to really sort of talk about hints and tips, how to get through it. You can do it. And you really can, I promise you. And I'll kind of share with you some of the stats, to give you a bit of confidence in going into this exam. And then we will start our revision. And then on Friday, we're going to do all sorts of revision, a lot of revision. So so I'm just gathering. If you haven't seen on Ed, I'm running a poll, what topic you want to focus on. Right now, I think linked lists are just a little bit in front, followed closely by pointers, and then strings and char. So, head over to Ed and have a vote if you're interested in covering any particular topic. It will be good to know where people feel the most uncomfortable, and then we're going to do lots more, more examples there. Also in week 11, we are going to run some revision classes that you will be invited to attend. And I will provide more information on how to kind of register for those and how to attend those in my Mondays or Tuesdays announcement in next week. So it's going to be pretty exciting, and we will next week also give you some revision problems, and we're also going to open up your, a prac exam for you as well. And also actually quite important is the My Experience surveys. So if you haven't done that already, it would be great if you can fill out the My Experience surveys. The surveys are anonymous. The feedback is really important to us. We genuinely use the feedback to improve the course for the next, lot of students, and hopefully, make things better so that it's, so it's an enjoyable course. I know that it's not an easy course to do. So how can we make it more enjoyable for students, and how can we make, things better as well for you? And improve the whole experience. So please fill out the My Experience surveys. I'll send another reminder as we go. And you should have received your assignment 1 marks. They are out. I think Shrey released them on midnight, I think, in the nighttime. So unless you submitted late, then yours might not be out just yet. Okay, do you have a week off, week 11 before exams in week 12? You ask a really good question, and I do, yes, I believe I think the exams actually start on Friday in week 11, but not 1511 exam is on the Monday. So yeah. It used to be, we used to get a whole proper week when I was at uni. It was so exciting. So absolutely. You're not as lucky now. You only get, I think, 4 days. So we will run revision classes on those 4 days. So hopefully you can, come in, and we're going to be working through problems in that time. Okay. Any other questions? Or how's everyone feeling? Week 9. And the big long weekend is coming as well, which will give you a little bit of space to breathe. Forums will be operating still. So, keep asking your questions on the forums. And there's no classes on Friday at all. So if you have a tutorial, there's no tutorials. If you have a lab, there is no labs, and there's no lecture on the Friday. And luckily, we don't have any classes on Monday. Okay, any questions at all before we start, before we get into the content, before we get coding? How is everyone feeling? I know it's week 9. Is everyone feeling good? Everyone's just not feeling. Everyone's done. Is everyone done? I can. Where do you find marks? Oh, okay. Assignment 1. You find assignment 1 marks in the same place that we find all our other marks. So if you go to the submissions page, and you will click on the blue bubble, that's the one that has all the, that's the one that has all the all the marking stuff. So you can see the rubric and the guideline, which didn't look very nice. I think Tom was trying to fix it, but we broke something else when we were trying to fix it. So it's like, seriously, when you're doing your assignments and you're so frustrated something's not working, that's us like every day. So it doesn't get any better. We usually fix something and have something else break, and we're just, yeah. But it's been working so far. Your page is refusing to load. Oh no, okay. Maybe Tammy, can you please go and check? Oh no, it's working now. Okay, don't worry, Tammy, you don't need to check anything. Thank you. Someone's come see, come say. Okay, so 50-50, great. Okay, good. Okay, yeah. So I think we've loaded up the submissions page, which is why it might be, I don't know, taking a little bit to load. I don't know. Who knows? Who knows what's happening? It is working though. So yeah, assignment 1 marks are out. If you see any mistakes or if you want to know anything, please let us know. Someone asked a question about magic numbers. I will let Tammy answer that question in the chat, and she will give you a more detailed answer in 200 characters, or maybe even over 2 messages. Who knows? The world is her oyster, but there is a reason. That we deduct marks for magic numbers. And if you have any issues, if you see any issues, just send us an email or send your tutor an email and they will forward it to us, because, sometimes there's a lot of students in this course and sometimes we may, there might be some issues. So it's good to nip them in the bud now, before you get ready for the exam as well. So that stress is removed from your life. So that's good. And before you got this adrenaline rush to get assignment 2 in as well. Okay. Okay, let's get started. Lecture 15. Yay. Okay, so I tried to go too fast again. Okay. So last time we kind of returned to the ice cream shop example. We built on it. We put together a linked list. And we did an example with inserting, traversing, deleting. So if you didn't understand it, the stuff that we're doing today kind of goes into the same thing. So don't worry, as per usual, I'll be rehashing things, talking about things a lot, drawing diagrams a lot as well. We also talked about using that leak check command to make sure that you've used free for all your malloc memory. It's just a way to compile with that command so that you can make sure that you've used free, and to check, that you've freed up all the memory that you've decided to malloc as well. And I did a speed run through the multi-file project, so we're definitely going to be doing that again, because to say speed run is probably an understatement of how I covered it off on Friday. It was just and done. And okay, so today, multi-file project, slower speed. I'm still debating whether we'll do basic command line arguments or whether I'll just show you what they are next week. They're not going to be examinable, so don't worry. And we're going to do abstract data types today. We're going to talk about the stack and what is an abstract data type. And we're going to implement it using a linked list to give you more practice of a linked list. All right, where's the code? The code is, as per usual, right here. I might let Tammy paste the link for the live lecture code into the chat. Hopefully I've set all the file permissions okay. So someone's asked a very good question. Are stacks examinable? And I will provide more details on Tuesday, but it's like a lower level of examinable. So, it might be like one of those short answer questions. And sometimes we'll have like one of the sort of further on practical questions that might use a stack. But you can probably, get some marks for it without using a stack. Yeah. Okay. So I just wanted to just quickly do a roundup because we keep talking about boundary conditions, and we keep talking about what should I think about when I'm making my linked list, or when I'm manipulating my linked list. So I just wanted to provide one slide summary, and that's kind of, these are the things you should ask yourself if they change, or if you need to consider them in your situation and in your problem. So one thing is an empty list. Does that change what's happening if you have an empty list? Check it out. If you have a list with one element, so does that change in the context of your problem? If something happens at the beginning of the list, so you're doing something with the head of the list. If something happens at the end of the list, so you're doing something with the tail of the list. And then also something is not occurring. So if you're looking for an item that's not in the list, if you want to insert a number after a number that doesn't exist, or if you want to delete a number that doesn't exist, or if you're looking for something that doesn't exist, have you taken care of it in your problem? So those 5 cases, when you have a linked list, try and run through those 5 things and make sure that your code and that your logic takes care of those cases, so that you've thought about it already. It's going to work, with your code kind of thing. So give an input of an empty list, give an input of a one item list, give an input where something will happen at the beginning, something at the end. And if, it's not in the list, you have to kind of really do nothing. All right. Okay, so back to multi-file projects, this time at a much slower pace, hopefully a more normal pace. So basically, big programs often spread out over multiple files, and last term, even our assignment 2 was spread over multiple files, this time only in stage 4. We gave you a little bit of reprieve, but that also meant that your file was quite large, and it was, it looked quite overwhelming to start with. So there is a number of benefits to using multi-files when you are working on big projects. And one of those is that improves readability, because it reduces the length of your program, because you can move some things out into other files. You can have different implementations in different files. You can also separate the code by subject, so you can have modularity of code. And you can also test and write the modules separately. And that means that you can have multiple people working on the same project, and they can be working kind of not on the same file. They each have their own file, so they can't really affect each other's, well, they can affect each other's changes, but that's a different type of testing altogether. So far we've already used multi-files because we've hash included, and every time we hash include, we're really borrowing code from other files, okay? So every time we take a header file, so the .h file is called a header file, we're using a standard library that C has provided, and it will go and find that piece of code and kind of implement it in our functionality. So in fact, we've been using multi-file projects this whole time. It's just been a bit of magic, and now it's about to stop being magic. Okay, so you can also hash include your own. So far we've hash included what C has for us, C standard libraries, but we can hash include our own, and that's what allows us to join, different projects together, and it allows us, multiple people working on different things together. And also this means that we can produce other code that, in other projects. So if I have, and you'll see how useful it is when I have something like a stack, and I'm doing, how the stack works, I can use that in other projects as well. Okay, in a multi-file project, we might have multiple header files, and this is a .h file. So usually we hash include our .h file using greater than, less than symbols. But if you're including your own header file that you wrote, not the standard C library ones, you include them in inverted commas. So in apostrophes, inverted commas, what are they called? Inverted commas, quotation marks, there we go. But I think they are also called inverted commas. No, quotation marks, we'll go with that. So that's your header file, and then you might have multiple implementation files to go with those header files. So you'll have, and that's your .c file where you implement all the functions that you've defined in your header file. And each header file that you will write will have its own little implementation file. So there's a header file and implementation file, header file and an implementation file. And then separately to that, you have your main.c file, and that's the entry to your program. We try and have as little code there as possible in terms of we like to call functions from that main file, and we don't like to do things and to do logical things inside that main file. We really want to take it outside to our implementation files. So what you work towards when you have those types of big projects is that I should be able to use the main file without actually needing to do any coding. I should just be calling out to everyone else to do my work for me. And the main file is sort of the king of the castle or the queen of the castle, either way. So, I see someone wants to talk about destroying a linked list. I will destroy a linked list today as part of the stack. So I will be destroying the whole linked list today. All the nodes plus if there's a root structure, the whole root structure. So yeah, so we will talk about it today. Okay, so the header file include in quotation marks, now that I've decided to call them that, your header file. It typically contains your function prototypes that will be implemented in the implementation file, any comments that describe how the functions work, any hash defines. So basically this is the instruction booklet that you give to someone who will code it, and they have to go off and they have to implement whatever's in this header file. So you've given them like the directions and instructions, a definition of what they need to do, and they need to go and actually implement it in the implementation file. So there's no running code. It's more like a definition file. So it's all your hash defines, all your function prototypes, and comments on what those functions do. Then the file that goes with that header file, so its very close sibling, is the .c file, even its twin, but a fraternal twin. I'm not sure if it's a good analogy, maybe. So it's fraternal twin because it's the one that implements everything. So you've got one who's the boss and one who's the implementer, one that's actually doing things. And that's the one where you implement the functions that you have defined in your header file. And then the main.c, and that's where you call out to everyone and you kind of make them do things. So let's switch over to our code and implement this structure, and I'll do it in a very simple piece of code, and then we're going to do it then we're going to do it again. We're going to use this multi-file structure for a stack in the next part of what we discuss. So exciting. Okay, so first of all, I've got a header file, and the way I know it's a header file is because it's called maths.h. The .h on the end is what tells me that it is a header file. So I'm going to do a maths module because I don't know, who doesn't love maths? So the header file will contain any hash defines and any function prototypes and any comments. So let's do 2 or 3 functions in here that we might implement. I've got a few in my example in the slides. We can do different ones. It's not a problem, whatever you like. Let's do some functions. Who wants to do, let's do simple ones just so that we can see how the multi-file structure works, but not sort of waste time on it. So would we need multi-files in the exam? Maybe in question 8, practical, maybe, and maybe there might be, like a short answer, like a multi-choice or short answer question. Okay, someone's saying absolute value. I love it. Yep, why not? Let's do an absolute value. Ooh, I love it when it does that. It really annoys me. It ruins my perfectly clean terminal. Okay, so if we do an absolute value, so I'll do a prototype for it. So this function will return an absolute value of a number given to it. Excellent, okay. Inputs and outputs, what would inputs and outputs be to this function? Powers, I like powers, that's a nice one. Okay, let's do a powers off, okay. This function will calculate powers off for a number. Excellent. And shall we do, let's just do a sum, because a sum is always easy to do. Sum of numbers, sum of two numbers. Why not? And this function that calculates the sum of two numbers. Actually, I haven't used a hash define. I'd like to use a hash define. What's something that we can use a hash define in? Anyone? Anyone? Okay. Yeah, I mean, but then I'd have to do a circumference. Which one am I killing to do a circumference? Oh gosh, Sophia, we're getting quite a good, like, oh, complex numbers. No, this is meant to be simple. I love it though. I love all these ideas. Let's do something really simple. Like let's just do pi, because pi is really simple. So any hash defines can go in here, absolutely any. And let's do, okay, if we have an absolute value, we would have to give it, and what do we, yeah, so you could do a hash define for gravity, speed of light. Oh, thanks, Bill. Function that plots and printf the graph out. Oh, wow, I'm so excited. Yeah, that's no, thank you. That's going to take up the whole lecture almost. Well, maybe not. Maybe not, actually. Oh, it could be fun. No, you're swiping me. No. Yeah, so all those physics constants and stuff, they're great things to hash define. Absolutely. Okay, and grab, yeah, okay. So inputs, if we do an absolute value, I like absolute value, it's really simple. So the inputs would be a number, and an output would also be a number. And then, oh my gosh, everyone knows a lot of formulas. I don't know if I remember all these formulas. Probably not. I didn't love physics as much as I loved maths. Okay, then powers of a number. Our inputs will be the number and the power we want to take it to. And the outputs will be what? The outputs will be the number, so the final number, the result. And then the sum of two numbers, the input will be two numbers. And the outputs will be one number, which is going to be our result. Okay. Yeah, it is possible to hash define a fraction or a division. Yes, it is possible to hash define that. Okay, good. Okay, so let's define we've got a hash define. Let's do some function prototypes for these. Okay, so we say that this one's going to return a number, so it's going to be int. I guess we'll call it absolute value, and we're giving it an int to play with. Yep. So that's going to be our prototype for this one. Prototype for this one is going to be calculate powers off. We said it returns an int, powers off, and it gets given an int number and an int power. Okay, great. Now next one, the final one, we've got our int sum, and it gets given two numbers. Int number, oh, that's int number 1 and int number 2. Excellent. Excellent. All right, so we've got three little functions here. Is everyone happy with our three little functions? So now that we have our .h functions, okay, we're going to head over to our maths.c, which is our implementation file, and we're going to implement these functions. Okay, so I've got three functions in here, and I want to actually implement these functions in here. So that means I'll actually be implementing what's happening in here. Okay, so I'll just do my brackets. So this one, and last of all, this one. Okay, excellent. Okay, so the first thing we need to do is right now, as per usual, we're going to include, I don't know, our stdio. I don't know if I'm taking anything in, but just in case. Okay, but now, because I'm using this as an implementation file of a particular header file, I have to include that header. So I include the header file on all .c files that use it, okay? So what that means is I'm going to hash include, and because it's my own header file, it's going to go in quotation marks. So maths.h, and then I'm going to close the quotation marks. What that means is I've now included my header file in the implementation files. Okay. And so where do these function prototypes, so the function prototypes always go in your maths.h. That means they don't need to go in the main.c, but what you need to do in the main function is also include your header, okay? Oh my gosh. Everyone knows my typing is it's just reducing and it's, okay, and then someone asked a great question in assignment 2. Once I've done something, I will usually remove my to do, okay? And so I'll remove it here as well because I've included. So every .c file that you have, the relevant header file will be included in it, okay? Both the main and the implementation file so that you know what to look for. And so when your main gets read, okay, it's going to read this hash include maths.h. It's going to go to your maths.h, and it's basically going to move this across into the main file, Neil. So what that means is it's going to include all of this information on top of that one. So this is what I mean about you really breaking up, you know, what you're going to do. So there's not as much things, you know, so there's not as much stuff clogging up each file. Okay, so let's do some of these. Okay, who's got ideas for absolute value? How are we going to implement our absolute value function? Or should we start? Yeah. So I'll wait for that. How should we do that? What do we think? So how does the maths.h know where the maths.c file is? Maths.h doesn't, but maths.c knows where the maths.h file is, if that makes sense. So the C files are the ones that refer to the header files, and it's not going to work unless you include your header file. Yeah. Okay, so someone's got some great ideas. If your number that you get given is greater, no, it's not, is less than 0. Is that less than 0? Yes, it is. My less or greater than is coming good again. Then I'm going to multiply it by -1. Excellent. Well done. Then number is equal to number times -1. Very good. And then I'm going to return my number. Okay, very good. Excellent. Okay. I'm just checking, going in the chat. How did I go the wrong way? No. This number is less than 0. Someone is killing me there in the chat. Are you trolling me? Okay. No, maths.h only has your definition. So maths.h only has the hash define and function prototypes, okay? Then your maths.c is the one that's going to implement the functions that you've defined in your .h. So the .h is inside .c. So what happens when I compile, and I compile all my .c files, okay? So when I compile this maths.h, it goes across, finds .h, takes all of this stuff, and then copies it across in here so it knows what's going on. So you will include your maths.h in your implementation file and also in your main file. So your header file is included in all of your .c files that might use it, okay? So how does it know? Because you compile it together, okay? And so it kind of, I see what you're saying. That is an excellent question, Kate. And I'll draw you a diagram in a second, okay? Once we compile it, I'll draw you a diagram how it knows things. Okay, so let's have a look. So what do we have? Where we were up to, okay, we got up to powers off. Okay, excellent. So how are we going to implement the powers off? What are we thinking? How are we going to do the powers off? What will we need if we're going to keep doing the power off? And let's not do huge powers when we try it off, because otherwise we're going to kill something. Yeah, a while loop. Yay, we get to use while loops again. Always exciting. Okay, okay, so whilst... Okay, so someone wants to keep track of it. Let's do it. So we've got some sort of count. I'll set it to 0. And whilst that count is less than my power, then I'm going to say number is equal to number times number. And then my count is going to be increased. That's right, our friend the while loop. Absolutely. Okay, excellent. And that should work, shouldn't it? Yeah, because I started the count at 0. Does that make sense? It doesn't really make sense to start it at 0, but it doesn't matter if it's less than, as long as I account for that. Okay, and then what are we going to return? We're going to return our number. Is that going to work? Yep. Yeah, it is wrong. That's right. It is wrong. Well done. What if the power is 1? Yeah, and you start with 0. Yeah, exactly. Absolutely. Yes. Oh my gosh. Yay. I'm so excited. Everyone, amazing. Well done. Okay, good. I was going to run it to show you that's going to be wrong. Okay, so who understands why it's wrong? Yeah, quite a few people seem to be. Tammy, can you poll people that understand why this is wrong and it's not working? Oh my God, the boundary case is fantastic. What if the power is negative? Oh my gosh, another great question. If the power is negative, then this does not take care of it. So we're going to assume, just for the fun of it, here in this particular thing, it has to be a positive power. But that is an excellent test case. That is definitely the way to break it, is to have a negative power. Fantastic. Do we understand why this is not going to work? Oh yeah, Tammy's running it. Oh, yes. Amazing. 100% yes. It's very resounding yes. Oh, it's only had 1 vote. Okay. No. Okay. I'll just quickly run through it because it's quite a few no's. So let's say I'm going to give this function 5 to the power of, okay, I'll start with exactly. I'll do 5 to the power of 4. Okay. Count is equal to 0. Great. Now here we're checking count, which means 0 is less than power, which is 4. And then here I'm saying number is equal, so that's going to be number is equal to 5 times 5, which is 25. Here my count is equal to that took me a really long time to do 0 plus 1, apologies, okay? So then we've got 0 plus 1, it's going to be 1, excellent, okay? And then I'll go back and I'll say, okay, is 1 less than 4? Yes, it is. But now I'm going to be doing number is equal to 25 times 25, okay? Because my number is equal to 25. So then I'm going to be, on my next roll, I'm going to be doing number is equal to 25 times 25, which is definitely not going to be the right thing, okay? And that's why it's not going to work, okay? Because I'm overwriting it each time. Okay, so I'm going to say here int result is equal to 0. And then we'll do this other one that you have also thought about. Okay, and what are we going to do? So we need to keep the base the same throughout the loop. Yes, exactly. So we could also, yeah. So let's do base is equal to number, and that's going to be our base one that we're going to multiply by, okay? And we're not going to change the base. Okay, so if we do it like that, then what can we do there? Oh, that's a good idea as well. We can store the input number into a new variable and call it multiplier. We could do that, absolutely. That's a great idea, actually. Yeah, let's do that. Okay, so each time we're going to multiply by number, and then here we're going to have result okay. So many new ways to do it, absolutely. Yeah, you absolutely. All of these are really valid solutions to this question. Okay, so now what it will do is it will say, okay, is 1 less than 4? Yes, it is. Then I'm going to say result is equal to multiply, which is my number 5, times the result, oh, which is 0. That's a bit unfortunate, isn't it? So it's going to give me 0 on the first thing, and then it's going to throw the whole thing off. Yeah. Yeah. So we really want the result to be 1 to start here with. And then we're going to continue. So then the next time you run it, it's going to be 5 times 5, which is what you want, and so on and so forth. Okay. Great. Okay, let's do the sum. The sum is easy. The sum is just, I'm really just going to return number 1 plus number 2. Excellent. Okay. All right, very good. Now let's do some calls out in our main function. So now I've switched to the main, and I do my usual thing. Int main void. Trying. Okay, here we go. Let's have our, oh gosh, indentation, terrible. Int number, throw me some numbers. We would, Sophia, absolutely, yeah. So we haven't taken care of all the edges, and we haven't taken care of negatives either. Okay, 10 and 42, I'll just take the first two numbers. And I'm going to have a double actually, so I'll take a double as well. Okay, now let's do it. Let's use some of our lovely functions that we have going. Oh, we could scanf, absolutely. And the world is our oyster. It's true, we could scanf. Okay, let's do the first one. Let's do the absolute value. Oh, we really should have a negative number, shouldn't we? Because we have absolute values. Oh, how frustrating. Let's make it -10. Well, it's not frustrating. It's really neither here nor there. I'm really just making a mountain out of a molehill. Okay, and okay, so the absolute value of %d is %d. And I'm going to call my function, which is called absolute value, and I'm going to give it number. Because I'm going to use a double to play with that hash define that we had. Yep, that's right. because the hash defined values in maths.h exist in the main.c file. So I'm gonna use that hash define that we did because we defined it, so we should use it. Okay, now let's do one that's using the other one. So yeah, and spelling printf, the power of, no, let's do %d to the power of %d is %d. I could confuse myself. I do need to, yes, well, good pickup. See, this is too many. I've got too many things going. Absolutely. So number first, yeah, to make up for that -10. Good. And then I'll call the function. In here, oh, I've not done us any favors here. Let's do 3. Let's do, what should we do? Number 2 to the power of, I'll do number 2 to the power of power. And then my function is called powers off. So I'm going to call the powers off function and I'm going to give it the number and I'm going to give it the power. All right, good. And let's use the last one, the easiest one. Let's do %d plus %d is equal to %d. And I'll do number 2. And then I'll call that lovely function I have in maths.c sum. So sum of number and number 2. Is that everything? I think that's, oh no, I haven't used my hash define. Let's just finally use a hash define just because. So let's do printf %lf. And here we're going to just do decimal plus pi. I'm missing a bracket. Of course I am. I'm always missing a bracket. Here it is. Yep. Okay, let's try it out. Should we give it a whirl? Should we give it a whirl? Okay, so to compile a multi-file project, I compile all my C files, okay? So that means that now I know that all of these C files belong together and then the .h files are included in each of the .c files, okay? So the way I compile it is I basically say the same way that we normally, so DCC, and then I'll say both, so maths.c, main.c, doesn't matter which order they're in, as long as you include both the .c file, not the .h. Okay, excellent, it compiles, amazing. And now let's run it. Okay, so the absolute value of -10 is 10, 42 to the power of 3 is 42, that's definitely incorrect. -10 plus 42 is equal to 32, and our decimal plus pi is equal to 6.28. Okay, so it's working, right? I mean, one function is incorrect and we can fix it because clearly we did not consider something, but can we, Tammy, could you please do a little poll on multi-file projects and whether it kind of makes sense? And I'll draw it out for you what happens when you compile it. So when we compile it, I'll do it whilst Tammy's running that next poll. Okay, my iPad's locked whilst we were talking there. Okay, so when you compile it, when I call the compiler out, what I do is I call it to compile both my C files. So what that means is I've called it to compile a main.c and I called it to compile a maths.c. All right. Now, each one of these files inside it has a hash include, and it includes a maths.h file. And this one also has a hash include, and it includes a maths file. So both of them, when you compile them, are going to reach out and take what is sitting inside the maths.h file and place it on top of this file. And same with this one. It's going to take this maths.h and it's going to place it on top into that file. So remember, all of this stuff is done for humans, okay? It's done so that we can make things more readable for us. It's not really for the machine. The machine doesn't care if the file is, 20,000 lines, but we do. It makes it very hard to read if it is like that. So what happens then is that we can separate it out, and then when we compile these two files together, then they reach out and they take this maths.h file, copy the info across, and we know that they go together because we've compiled them like that. Okay, so let's see how we're going in our polls. Not too bad. Not too bad. That looks quite good. And again, this is not going to be a hugely examinable thing. So as I said before, it's going to be, you're going to use it, well, if you've done stage 4 of the assignment, you're going to use it there. Of assignment 2, there might be, a short answer question, so like a multi-choice or a 1-mark question about it, or 2 of those, depending. And then maybe question 8 in the exam is going to have it. All right, fantastic. I think it's a really good place to take a little break before we, get into abstract data types and before we get started on learning about the stack. There is 20 short answer questions and 8 coding questions. You submit all the files, kind of thing. There should be an instruction in your there should be an instruction in the assignment with the exact command to submit all the files. Yeah, so when I compile maths.c, main.c, I'm pretty much making one big thing, and they both need maths.h too. So they both include maths.h. So they're going to both reach out and see what's inside there and access that. How much technical jargon? Not like, no, more want to know if you can read code, understand code, and understand what's going on. The exam has 2 hurdles, and we're going to talk more about them on Tuesday. Absolutely, yeah. Okay, so let's take a short 5-minute break, and then we will come back for stacks. Woohoo! All right, here we go. We're back. Sorry about that. Everyone got to see me chatting to Tammy. I was in such a rush to get off because I knew my dogs were about to start barking a lot. So I was like, no, get off, get off, get off. And then I was like just discussing the very loud barking that was occurring behind me for 5 minutes. But now we're back to quiet sleeping time. There's one sleeping right behind me as we speak. All right, guess what? We're up to the last topic that I will cram down your necks. How exciting. Okay, let's talk about abstract data types. And you will use these later on in computing quite a bit. This is really just a basic overview to kind of give you a little bit of a look-see at what's going to happen, a little peek at what's coming. Do you love computing? Do you feel more neutral towards computing right now? Or did this, or you just can't wait to get more into it? All right, so what are abstract data types? So they're data types whose implementation details are hidden from the user. What this means is that I know the rules of something, how it works, but I don't really know how it was implemented, and I don't really care how it was implemented. And so a really great example of this, and one of quite a commonly used ADT, is something called a stack. So a stack has set ways in which it works, but it can be implemented using a number of ways. And what that means is I could implement it using a linked list, or I could implement it using an array. And that's hidden from, the actual functioning of it, because even if it's linked list or array, it works in exactly the same way. It works like a stack should. So a stack has a certain set of rules, and then we can implement it in whatever way we want. And whoever is using our code doesn't need to see how it was made. So we've applied this, little bit of a curtain over how things are actually working. They really just want to use it. It's the same way that, you're watching, your TV, but you don't really know how the TV is working, how all the channels are coming at you. You don't open up the TV or to the inside, see how all the connections are made. So all of that is abstracted from you, and you don't care as long as you can, watch TV. So that's kind of that level of abstraction. And the same with a stack. I don't care how it was implemented. I just care about how I can use it. So a stack is really a last in, first out structure. Okay, so what that means is I make a stack of dishes, I make a stack of books. Okay, before this lecture started, I was like, I'm going to make a huge stack of books in front of the camera and then pull the books out. Except when I did it to try it out, they fell all over my feet, and then I was like, I'm not doing that in the lecture because then just I was yelling out and stuff, so it was not that pretty. So we won't do that. And dishes, I thought, well, I'd break a whole bunch of dishes. So maybe we won't do that either. But basically, you have a stack of dishes or you have a stack of books, and you can't remove things from underneath. You're just going to take the top thing off the stack. So that's how a stack works. Basically, you build it up from the bottom up. So you got, you keep kind of building, and you only have access to the top thing. Okay. So before we talked about, having these function calls in memory. And if you remember, your computer memory has a stack and a heap. And so a stack, and if the famous website Stack Overflow, it's basically called that because of a stack overflow, because you just kept putting things on the stack. So when we make function calls in any sort of main that we're running, what we're doing is we're kind of using this stack memory, and that's how memory works as well. Well, the stack part of the memory, there's also the heap, which is our malloc memory. So basically, if we have this really, really basic thing here, okay, you kind of go into the main, and what happens is the main starts running on line 3, and so that's your first thing that starts running, and that goes on the bottom of your stack. Then over here on line 7, you call a function called square number. So what happens is this function goes on top of the stack now because you've just called it, and only this function is now accessible, okay? So that means you're going to go straight into square on line 12, and you're going to start doing here. you're going to go into line 13 and it's going to call a function called change, which means on line 13, change is the function being called. It goes on top of the stack, and now it's the only function accessible for you. So you go into your change function, and when you hit line 18, you return the number +1 back to here. That's when you take the change off the stack, and then your square becomes available. And then when you return here back to your main, then you take the square off the stack and only your main becomes available. So it's like you're pushing onto the stack and you're popping off the stack things, okay? And that's how stack memory also works. So when you declare all your variables, the way you use them, it all kind of functions in the stack and moves around. And as you go further, you'll learn, how to like optimize your code and make it more efficient as well. So the idea of a stack is really just that. It's an idea. It's not like a physical, thing that we, kind of build up or whatever. It's an idea of how a stack works that we then implement in our code. So can you think of anywhere that a stack is applied in our everyday interactions with computers? What do you guys reckon? Can you think of anywhere that that's something that would work like a stack? Can you think of anything at all? What does Control X do? Does it cut? Yeah, oh my gosh, undo. Yes, undo is a great example. Folder structures. Yeah. Web browser back button, absolutely. Yeah, so it only goes back one step and it goes back to the top of the stack. So you're popping off whatever you're using. Great. So definitely undo and redo. Links within links. Yeah, if you go back, I guess it could be. Yeah, so some really good examples. And if you just think of the most basic is your back browser button, because that kind of keeps a stack of where you've been, and every time you press back it only goes one step back. Same as undo and redo, one step back, you pop, well, mostly undo because you need to be popping stuff off and going backwards. So a stack behaves in a certain way and it's defined by a certain set of rules. I can do it using arrays, I can do it using linked list. No one cares how I implement it as long as it's implemented, basically. So let's implement a stack, and we're going to implement it as a linked list, so that we can practice our linked lists again, and so that I can show you how to delete the whole thing as well. So in a stack, we usually have two special terms. One's called a push. We push onto the stack, which means we add an element onto the top of the stack, and the other term is pop. We pop off the stack, so we take the top element off the stack. All right, so today we're going to look at creating a stack, adding to the stack, taking from the stack, count how many things are in the stack, and destroy the stack. And really, as you see this, as I go through the next pictures, in the next few minutes, you'll see that it's very close to the example of the ice cream shop that we were doing, in the way that it's using a linked list, okay? So hopefully it will kind of relate back and forth. So a stack is really a structure, okay? And we will define it in our header file, and I've provided you with a header file with all the functions defined that we're going to do. So if we do a linked list implementation, okay, let's talk about what we're going to have. So first of all, we're going to define the structure itself, and that's going to be your struct stack. And all I want to know in my stack is I really want to know what element is sitting on top. And you can see already, this is where my nodes are going to start. This is where my linked list is going to start, and it's going to keep going. Now I've got one other thing inside my stack. I don't have to have it. It's up to you, if you want to implement your stack like that. And we always implement it based on what the problem is asking and stuff. There's ways to keep track of a few things inside the stack, but I've got an in size in there, I don't know, for fun. And basically it's the size of the stack. So how many things there are in the stack. And then I've got this struct node top, which is the top element. So I want to keep track of what's sitting on top of the stack because that's what I'll be taking off the stack. So the head of the list. And each element, so off the stack, is going to be defined as a node. And you're familiar with this data structure from our beautiful linked lists. You've got an int data and a struct node next to see how they all link up. Okay, so let's say we've got our main file, okay, and it looks something like this. So inside our main, we have a struct stack, new stack, create stack. Oh gosh, you're very good at, kind of thinking it through, and we'll talk about actually writing this code in a second. So if we're creating a stack, all we're going to do is we're going to create a space for a stack. Yep. And remember, I'm going to malloc some memory for it, and I'm going to return the address of where I created this memory. So this is going to be called new stack. Then if I move to the next thing of pushing onto the stack, let's say I push onto the stack, I say what stack I'm pushing onto, so this new stack that I created, and I'm going to push 11 on. So that means that 11 is going to go on, and 11 is now going to be my top, okay? So it's going to be the head of the list, my top element. And again, I'm going to create the node. I'm going to place the node at the head. If I keep going and I push onto the stack number 12, what's going to happen is I'm going to change the head of the list, and I'm going to put the 12 on top of the stack, so on top of the 11, and then that's now the bottom, that's now the top. Then if I add 13, again, it's going to be added onto the stack. So I'm going to just place it on top of the stack, and this now becomes my top element, and last in, first out. So that's going to be the head of the list now. And then if I add 14 on, then 14 is going to be pushed onto the stack, okay? And it's going to become the head of the list for me now. Now, if I start popping, I will pop off the stack. The top element is going to get popped, and I'm going to say what it is that's going to get popped. So 14 has just been popped. And then if I pop again, then 13 is going to get popped because it was the head of the list. So it's going to get popped because it's the top of my stack. Okay. Tammy, could you please check if that makes sense? Just the theoretical explanation of what a stack is and the fact that you last in, first out kind of thing, kind of structure. So Tammy, if you could please do that. Yeah, so head of the list is going to be your top of the stack. And then we'll switch over to the code to actually write the code for it. Yeah. So stacks are indeed fun. Yeah, so they're LIFO, last in, first out. Yeah. I don't know why I said they're indeed fun. They are indeed fun, but that was not the question. Just too overcome with joy about stacks. Haha. So a stack is not just a linked list. I'm implementing the stack using a linked list, but I could also do it using an array. So I'm implementing the idea of a stack. And in certain cases, so like using that web browser button, I'm keeping these nodes as, as elements of my linked list. But in fact, I'm just using the idea of the stack. So the last thing in is the first thing out. So when I go back, I'm just going back by one. So it's not just a linked list. You could do it using an array as well. You could do it you can use other things to implement it as well. So it's really just this idea that the last thing in is going to be the first thing out. So how do I, make that happen? So that's how a stack works. And then how I implement it is up to me. So it's not necessarily just a linked list. It's just what I'm going to be using in this instance to do it. But I can also do it using arrays. As long as I have this kind of idea of using a, where the top of where the top of it is my element that I will be the last one out, and I add to the top of the stack each time. So basically that's what's happening. Yeah. All right, excellent. Let's implement it. How exciting. See, a few people still doesn't, yeah. So abstract data types, it takes a while to wrap your hands, or even your head around it, because I mean, they are abstract, right? So you're abstracting all meaning away from what they're actually doing. So it's quite a hard concept to grasp, really. So don't worry if you're not quite 100% on board with a stack. That's okay. It's not, it's not a huge part of the exam. It's just a little part. So don't, I don't want you to worry. It'd be quite harsh to, and that's why I wanted to implement it using a stack to give you, using a linked list to give you a little bit more practice using linked lists as well. Okay. Aha, well done. Okay. So Sabrina, well done. Yeah, popping will be freeing the memory because I'm going to get rid of that node basically, which means I'm going to free the memory. And then when there's nothing in the stack, maybe I'll destroy the stack as well. And that means I'll destroy my whole container that I kept all my nodes in as well. And if you think back to that ice cream shop example, that's me destroying the ice cream shop, right? So destroying all the flavors and then destroying the shop as well. Okay, so let's have a stack.h, and that's going to be our header file for the stack. And inside it, I've got some functions. They are struct stack create. So I'm going to create the stack, which is creating my container for that stack. And then it might be, then I'm going to push onto the stack. So adding elements onto the top of my stack each time. And then I'm going to pop off the stack. So I'm going to take the top element off the stack and then I'm going to look at it, see what it is. And then I'm going to get rid of it or whatever. And then I've got a new top of the stack. Okay, then we're going to just do one for fun, size of the stack. Why not? Just so that we can use that in size that I've got inside. We're going to do a destroy stack so we can see everything destroyed and freed. Freedom. And then we're going to do a print stack just because why not? That's the best thing to do, isn't it? Now, I've realized also that I'm missing a main.c file. Okay, excellent question. Can we insert an element between two stacks like we do in linked list? Okay, this is an excellent question. And we can't do that because the stack, the idea of the stack is that you always add things on top and you always kind of, you remove things from the top as well. So you can't add things into the middle of a stack. And that's when you kind of have this idea of a stack. So it only can work in a certain way. And then you implement it using whatever it is that you want to implement it with. A great question. Excellent. Now I've realized I don't have a main.c file for my stack. So I'll just make one as well, just so that we can, okay. And I'll close these ones so it's not super confusing. Okay, so let's do this stack list and then we'll go on. So I'm in my .c file. So what I'm going to do is I'm going to include my stack.h in my quotation marks. And I'm also going to include standard library for malloc, and I'm going to include my standard input output for printing as well. Okay, so I've got a stack structure itself, and that's going to be my beautiful structure that will house all of my nodes, all of my dirty plates in the stack, or all my books. I don't know why they have to be dirty plates. They can be clean plates as well. I'm not sure why I feel like they should be dirty. So the structs, the first one is just creating a so the stack is just really going to be where I house everything. So it's going to be my main element, okay? And inside it, it's going to have a size and it's going to have a top node, okay? Now this is of type struct node, okay? And struct node has inside it some data and a next, so something that you're familiar with. So basically the top, that's going to be the head of the list in here. So this is really the head of the list. And then you have all your different nodes moving off here. And then each time you add an element in, you actually have to change, you insert it at the head of the list. as opposed to the tail, So here I'm appending it, which is not the way you do it in a stack. So in a stack, if I add a new thing, I would push it in here because then I want my head to be pointing here and this to point to here. I don't know if my diagrams are getting worse or what's going on. Not sure. Okay, so we've got our node and we've got the stack. So let's do the first thing. Let's create the stack, okay? So if we create the stack, then we will return the memory address of that stack. Yeah, so we're going to return the memory address of this top bit over here. So we're all quite familiar with building up this beautiful first thing. So let's do that. Okay. Let's do, what do we think we're doing? Okay, what do we reckon? How do we allocate some memory to our stack structure? Oh, I just combined it, a stack. It's even better. What do we reckon? It's quite a delay today. Yeah, let's malloc some memory and create our beautiful, and I'm going to do the lines of code as we go here so that you can see what we're doing. So I'm going to delete all of this. I'm going to erase it, erase it, erase it, erase it, erase it. Okay, so I'm going to malloc some memory. I'm going to call it a new stack, and I'm going to malloc some memory for it. And I'm going to give it malloc size off, and it's going to be size of a struct stack. Now brackets, brackets, okay, and a semicolon. Excellent. So we've allocated some memory to this place. So what that has done is that has created, malloced some memory for me, and it's done it as a stack. So that means it's got a size here, which is an int, and it's got a pointer top here. Okay, and this is called new stack. Okay, so now I have a new stack that I can add things to. Excellent. Next, I'm going to check, and we haven't done this for a while, so I'm just going to bring this back because just to remind you, because I've malloced some memory, I don't know if I've got enough memory to actually make this structure. What if I've, been using memory willy-nilly and I have nothing left? So I'm going to check, and remember, if there is not enough space and no address is returned, so if there's not enough memory to create this node, a null is going to be returned. So I'm going to check if this new stack is equal to null. And what that means is if nothing was created, then inside this new stack variable, it's going to be a null. So I'm going to check if it is, and if it is, that means that there wasn't enough memory. Okay, and if there's not enough memory, I mean, really, it's time to go home. We're all done here. Okay, now this is not going to work, is it? Because I'm returning an int here, but I'm saying actually it's going to be a pointer. So I'm going to do something a bit different here, and I'm going to exit out of this, exit out of here by using the exit command. Don't worry about this for now. I've seen a few of you in your code and your assignments using exit. But anyway, okay, so we've checked whether or not there's enough memory, and let's say there isn't. So now we kind of accommodated that case, and now let's initialize the stack that we created. So right now it's sitting empty. There is nothing happening. We don't really know anything. Okay, so when I first create this stack, what's going to be the size of my stack? What's going to be the size of my stack? What do we think? What do we reckon is going to be the size of my stack? Yeah, 0. There's nothing on there, so it's going to be 0 when I first created, and then I'm just going to keep increasing it each time so I can keep track of how many things I have. So there's 0 things in my stack. All I have is the container to house things, but I have nothing yet on this stack. I've just created this idea of the stack first. Okay, and then my top element is, there's no elements, so it's going to be equal to, it's going to be null. So what I've said here is that this right now is equal to 0, and this right now is going to be going to null because there's no elements there at all. Okay. Okay, someone's asked, why do we need to check if there's enough memory for stacks but not commonly for linked lists? You should actually always be checking if there's enough memory every time you use malloc. It's just that we've been a bit cheeky and haven't really been doing it. We just assume there's enough memory because we're not doing anything intense. So I thought, just remember that you might have a case where there's no memory. So that's really why I put that in there. This is just kind of taking care of any errors that you might have, creating more robust code as well. Yeah, exactly. As Tammy said, it's not that we don't need to, it's just that we haven't been. Okay, and then we return this new stack that we've created. Great. So what we've done now is we've returned this, the address of this stack. So we're ready to go into it. Okay, we're ready to push onto the stack. Okay, so let's do this function that will push items onto the stack, which means really add items at the head of the stack each time. Okay, so when I'm pushing onto the stack, first of all, I'm going to allocate some memory for the new item that you will push on. So what that means is I want to create a little node that I'm going to push on. So what I'm doing here is I'm really just making a node, and the node is going to have some data, and then it's going to have this next thing going for it as well. So struct node new node, you will recognize this code from our linked lists. I'm going to malloc size struct node. So what I've done is I've created just a little node with all the elements in it. There's nothing in them right now, but I need to fix them up. So again, you see how I've now that you've said that, I'm going to check again if there's enough memory, and I'm going to do it by saying if. That's probably not a good idea to hold that in my mouth whilst I speak. If new node is equal to null. So again, if there wasn't enough memory to create this new node, then I'm going to say there's not enough memory, and I'm going to exit out of here. All right, then the next thing we want to do is we want to initialize it. So we want to place something inside this data, and we want to have something inside here. Okay, excellent. Now I have passed this push onto the stack. I've given it the stack that I want to push onto, and I've also given it the item that I want to push onto the stack. And I might be operating a whole bunch of stacks, which is why I have just one push stack, and then I might be doing something else. So if I'm pushing onto the stack, I'm going to add it to the head of the list. So let's initialize it first, actually, before we go. Yeah, so stack. So the struct stack top contains the pointer to the head of the list. There we go. I've said it without sort of. So we've got new node, not new stack, new node. The data element is going to be equal to item. So whatever number I've asked it over here to put inside this node, okay? And I want to place this node onto the head of the list, because every time I want to add it to the top of the list. So new node next is going to be equal to the current head of the list, and the head of the list is my stack top. Okay, so the stack right now is called S. That's what I've passed on to. I know, not a particularly great variable name, and it's sitting on top. Okay, so what this means here, let's go over this code in a diagram so you're not being thrown by it. What it means here is we have new node data is equal to item. So let's say we gave this command over here, and we've said push onto my new stack and push the number 3. Okay, so if I've given this command, then what happens is it goes here and it says struct node, new node, malloc size off. Okay, so what that's done is created this thing here called new node. That's where the address of it is, and it's got a data and a next. Excellent. I've checked for memory, and then I've said initialize the new node. So I've said new node data is equal to item. So place this inside the data. Okay, so I'm going to do now that 3 is going to go inside here. And I've said my new node next is going to be equal to the head of the list. Okay, so S top. So whatever is in here, it's now the head of the list. So I'm going to be going like this. Okay, so Jeremy, great question. You do have a new stack, and then when I passed to a function, I've called the function push stack, and I've said it's going to be stored, the new stack is going to be stored inside this S, okay? So because remember, when we pass things to function, it makes a copy of whatever is stored in that variable. So I'm just holding it inside S. If you feel more comfortable, I can change it to new stack as well. So just let me know if you want me to change it. Okay, so then we've pushed onto the head. Okay, so now what we want to be doing is we want to correct the stack by changing the head and the size. So let's do that, okay? Okay, so if we're gonna fix up our size is stored inside the stack, yeah? And it's stored inside the size component. So all I'm gonna do is I'm gonna take the size and add 1 to it because I've created a new node. So each time I create a new node, I'm going to add 1 to the size, okay? And then I'm going to say that I want my top to be this new node that I created. Yeah. Yeah. Look, if you don't want to check for this, we don't have to check for this, okay? I wanted to once again underline what it means to have null as well. Someone's asked, will using a linked list in a stack limit the way we can use the linked list? We can't put elements at the end of the list. Well, not necessarily. So we're implementing the stack using a linked list. But if I want to implement the stack, then what it means is that the problem that I have is a problem where things are added to the top and taken off the top. So the last thing added is the first thing that I want off, which is why I'm adding things at the head of the list. Yeah. So we're the ones that are creating these, well, it's not us, it's these abstract data types come with their own rules, and we implement those rules using a particular data, using a linked list or using an array and whatever else. Okay, we've pushed onto the stack. That should do it. Actually, hang on. Do we return anything? No, it's a void. Okay, so what that means is we've pushed something on. Hopefully, we've made these connections. So let's run through the code and the drawing of what it does. People are very uncomfortable with this. I'm gonna comment it out if it makes you so uncomfortable. Checking for null. So let's go from line 47, okay? So I'm going to delete this and just show you again what it's doing. Okay, so let's say we have this structure here, this new stack that we created in our create stack, and the top is null, the size is 0, fantastic. We've now said the command, I'm just going to change that because our command is push stack. So I'm going to call push stack. And I'm going to call it with new stack. So push onto the new stack and push the number 3 on there. So on line 47, the first thing I'm doing is I'm creating a node. So I'm mallocing some space and I'm creating an empty node. And I've got the address for it. It's called new node. Okay, excellent. We're familiar with that. Then I'm saying new node data. So whatever's sitting inside this data component here is going to be equal to item. And this is the item because in my push stack, this is the stack here. So this one is the S and this one here is the item. Okay, So if I push this item on, what that means is I'm going to add 3 into my data on this one. And here I'm saying new node next is equal to what's currently sitting at the head. What's currently sitting at the head is this null here. So I'm going to add the null in. And then I'm going to go on next and I'm going to correct the size of the stack. So I'm going to say whatever's inside this size is now equal to whatever's in here plus 1. So now that's equal to 1. And the top of the stack is now, right now it's still at null, but I'm going to point it to the new node. So I've gotten rid of this connection and I'm actually pointing it to the new node. Okay, so that's how we've pushed onto the head of the stack. And now if you note again, if we run this command again, so let's say we're going to push stack, we're going to do new stack, and I'm going to do the number 5, let's say. Okay, so if we run through the code now for the next one, let's see what happens. So the first thing we're going to do is we're going to create our node. Okay, I'm going to create an empty node with enough space for those things. Excellent. And it's going to be called new node. So this is no longer called new node now. Okay, I'm going to then say new node data is equal to item. So whatever item here I've centered is now going to go and sit inside my node. New node next is equal to whatever's currently sitting at the top. So what that means is right now stop has the address of this node in here. So this node here. So that means my next is now going to be pointing to this node. Yeah. And then my size of the stack is going to increase by 1. So I'm going to add 1 here. It's now going to be equal to 2. And my new top is going to be pointing to the new node. So now I've said this is going to point to this one. So it's me adding at the head of the list each time. And then I'll be taking off the head of the list. And because in a linked list, the easiest thing to do is really take from the head of the list because you know where the head of the list is. You have to traverse the whole list to get to the end usually. So it's not as easy to take from the bottom of the list. Okay, let's pop off the stack. Okay, I'm going to come here and Tammy, maybe whilst I'm doing popping, can you ask if pushing the code for pushing makes sense, please? Can you please poll? Thank you very much. Okay, so there's a boundary case where I might have an empty stack, okay? And if I have an empty stack, there is nothing to take off it. So what that means is if this here top is pointing to null, I'm actually going to dereference a null pointer because it's an empty linked list, okay? So I'm checking really if the linked list is empty. So what I'm going to do is I'm going to check whether it is empty. And it is empty if my stack size, oh my gosh, struggling, is equal to 0. Okay, that means that there is no plates on there. So you're not gonna, and remember the stack is called S in this case. So if the size of the stack is 0, that means there's nothing to pop off the stack because there's no plates on my stack. So I'm gonna come out of it. Okay, so now let's pop something off the stack. So that means I'm going to take the head of the stack and I'm going to point it to the next thing. Okay, so I'm going to have struct node new head and it's going to be equal to the top element. Okay, so I've said that this top element here is going to be equal to new head. Okay, then I'm going to say, and I'm doing this in multiple steps so that you can see exactly what happens, okay? So there is no lab exercises to practice stacks, okay? But there's going to be potentially some in the revision exercises, and in the prac exam, there's going to be a question that uses a stack that you can maybe practice with. But look over the code for what we wrote in the stack, and then you can implement it in the context of that question in that prac exam. Okay, so we've got the pop number is going to be whatever is sitting inside. I shouldn't have called it new head. Oh my gosh, let's popped head. And the pop number is equal to my popped head. but whatever's sitting in the data of it, okay? Okay, then I want to change whatever the top of the list is, okay? So what I want to do is I want to say what's now going to be at the top. At the top, I'm going to have my top next, okay? So I'm going to really skip this node, which is the top one, and then I'm going to go to the next one. That's now going to be the top of the head of the list. And because we're implementing the size, I'm also going to subtract 1 from the size if if I'm going to be subtracting a top node. So my stack has now gotten smaller. Okay, so I've got this node. I've now bypassed it. So I've now drawn from here to here. Now I want to free it. It's ready to be freed. It's ready to be set free. So I'm going to free it by saying free, and I'm going to free the popped head. And after I've freed it, I'm going to return the popped number. So that's going to be that top thing from the stack. So let's go over and draw it so it hopefully makes a little bit more sense. Okay, so let's say we've got these commands here now, okay, and we have now a new command. Okay, so now we're saying pop stack, and I just give it the stack. So let's say I've called pop stack new stack. Okay, so what we're doing here is on the first line here, we're checking if the size of it is 0. Is the size 0? No, the size is 2. That means I have something to pop off it. Okay, that means I'm going to skip this and go down here. Okay, let's do it from here, from the top. I'm saying I want to take the top element, the head, and I'm going to call it, and I'm going to put the pointer inside popped head. Okay, excellent. Then on the next line, what I've said is I want a number. Okay, so I'm going to say int popped number. So my popped number is going to be equal to whatever's sitting inside this popped head data. So it's going to be this here. So that means it's going to be equal to 5. Excellent. Okay. The next thing I do is I need to really get rid of this node now, and I want to point it to the next one after it as the head. So the S top, whatever address is sitting in my stack top, is now going to be S top, which is this one, next, which is this one. So what I'm saying is this is going to be my new address in here, okay? The next thing I do is, because I've gotten rid of this node now, I've bypassed it, I'm going to make the size of my stack smaller by 1, okay? So that means I'm going to do -1 here. It's going to be equal to 1, okay? Then I'm going to free this popped head because I don't need it anymore, so I'm going to get rid of it. Goodbye, popped head. And I'm going to return this number over here that I've popped off the stack. Excellent. So now that's ready to go. Now, what do you think we're going to return here if we do the size of the stack? What do we think we're going to need? What do you reckon? If I ever call for the size of the stack, what should I return? Because I'm keeping track of the size of the stack each time. What do you reckon I would need to return? Yeah, I'm really just going to return the stack size, okay? Because there's nothing, yeah. So I'm going to return whatever is, my dog was not impressed with that. Okay, I'm just going to return the stack size because in here, I'm keeping track constantly of what the size of the stack is. Okay, let's do a quick function to print and destroy. Let's do the print because the print really lets us see what's going on, and then we'll have time to destroy the whole thing. Okay. So, oh, we're getting really good with, surely we're getting very good with printing a linked list, aren't we? How are we all feeling about printing a linked list? Everyone feeling good about printing a linked list? First of all, I want a... I think my dog is over this stack. Okay, current is equal to the head of the list. So remember, the head of the list is sitting inside my S top. This is where the address of the head of the list is. So I've said my current is equal to the head. Now I'm just going to move through the current. So whilst current is not equal to null, I'm going to pulse through this list. The stress of it all. Hold up a second. Sorry. Let me just hold on a second. All right, like that never happened, okay? Dog is feeling the pain as well. The dog is done. He couldn't get to the end of this lecture, which just makes me so sad. I thought we were on the same page when it came to C, but clearly not. Okay, so whilst current is not equal to null, okay, we're going to print out whatever is happening in there. So we're going to print F. So we're going to print F, and we're going to print out the number, %D, new line, because I just want to pulse through and print out whatever's in the stack. So current data, okay? Oh, Tammy, my goodness, look at you go. Oh, and Lewis just popping another abstract data type in there. Love it. Okay, current data, and current is equal to current next. Fantastic, and that should print us a beautiful list. Okay, finally, the piece de resistance. How on earth do we destroy the whole stack because we're over the stack, okay? So we're going to destroy the whole stack now, and then we're going to run main with a few things going and see what's going on. All right, so one thing to consider in here is that every time we're popping off the stack, we are actually freeing that node, okay? So once we free all the nodes, if we just keep popping, then that means we're freeing all the nodes out, and then the only thing left to free is our new stack, the actual stack structure. So this destroy stack is going to be really us moving through the list, okay, until we finish all of our nodes, okay? So there's a few ways to do it, okay? Yeah, and we're going to finish with free S, basically. That's right. Like, I feel like what was that film with the whale? With Free Willy. There you go. So if you think about it, we've made this stack quite easy because we're keeping a size of it. So instead of like traversing the whole thing, setting the current, and you can do it. You can set the current to the head of the list and remove them all one by one. But you can also do whilst S size is not equal to 0, okay, because I'm keeping track of the size of my stack. So I'm just going to pop from the stack. So I'm going to pop from the stack S, and then I'm going to free the whole stack. Done, okay, amazing. All right, we're ready for our main. The main has nothing in it, so I'm just going to quickly do a main because I forgot to do a main, and then we can see it in action. How does that sound? Does that sound okay for everyone? Throw some numbers in the chat for me, please, that I'm going to push onto the stack. Okay, so I'm going to include, and I'm going to also include in quotation marks my stack.h because I've defined it as a multi-file. Okay, and then I'm going to start my int main void, and let's do some stuff to the stack. Okay, first of all, we're going to start by creating a new stack, and you can hopefully recognize, this type of structure is what we've been doing for the last few weeks, creating this root structure just like in your airport. And let's push some things onto the stack. Okay, push stack. We're going to push onto the stack number 42. Everyone is very keen on the meaning of life. Who's read The Hitchhiker's Guide to the Galaxy? Who's read it? 1000. Oh, 1511. How nice. 24. Oh, pi stack. Oh my goodness. Okay, fine. Let's do a pi stack. I love it. 3. I don't know why. I could just copy this and not just type it all the time. Okay, 1, 4. Okay, oh, we've stacked on quite a bit on here. Amazing. All right, great. Let's print it out. So let's print the stack. And we're going to print out this new stack. So we're giving it the address of where the stack is. Okay, now let's pop a few things off, shall we? Or should we just print it and call it? Let's print it first and see that. Let's compile it and see that it actually works. How does that sound? We haven't actually compiled it first. So I'm going to compile it, dcc stack.c and main.c. O stack. Because it's called stack list. Okay, I'm here with you. I'm like, what's going on? Okay, because I called it a list. Okay, oh, it compiled. Okay, so if we try and run it, it's going to print out our stack. So note how it's printing it out. The last thing in is sitting on the top, yeah? Which is what we want, 4, 1. So we put in 42 and it goes to the bottom of the stack. 1511, it goes on top of that. 24 on top of that. 3 on top of that, 1, and then 4. So the last thing we put in is the first thing that we're going to get to take out. Okay, so now let's pop something off this stack. Okay, let's pop stuff off, printf, and let's popped off %d, and I'm going to call the function pop stack, and I'm going to give it my stack to pop from, and then I'm going to print it again. Okay, let's try that. Compile it, run it. So I've popped off 4, so now note that the 4 is now no longer here, and my stack starts at 1. 1, 3, 24, blah, 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 blah. So every time I've popped off the top. Now note if I destroy the stack, so if I run my destroy stack, destroy, what's the function called? Destroy stack. It's actually called destroy stack. What do you think if I destroy this stack? What will happen if I then try and print the stack? Do you think this will work if I do it like this? What do you reckon? Do we think this will work if I destroy the stack and then I print the stack? Yeah, yeah, definitely. You'll definitely get an error. And the reason for that is once you destroy the stack, you've destroyed all of this. There is null there. There's nothing there. So you're going to have a bit of a problem. There's nothing really there to see or to do. There is no stack. So if we compile it, you can see that it's going to just go crazy for you because it can't access anything. It's called the print stack, and the very first thing it does when it tries to find the head of it, it's going to access a null pointer, and the error is malloc use after free. So you've tried to access something that doesn't really exist anymore, and you might as well just stop right now. Okay, so once you destroy everything, the whole structure, there is nothing there to access. So it's going to give you an error. Okay, what happens if I, pop off the stack? Let's pop the stack again. And then I'm going to push onto the stack again. And I'm going to push someone 81. Let's push 81 on. And then I'm going to print it again. So it's going to give you then compile. I didn't mean to clear. Run. So it's going to give us this beautiful, so we've popped off the 4, which is the top element that there was. Okay, I've popped off the 4. And then, then I've got, because I printed it here. Okay, so I printed out my stack. I'm like, oh my gosh, that's not right. But that's because I did it terribly. I should have done a new line or something. So that's my next one with the 4 popped off. Great. Then I popped it again, which means I'm going to lose the 1. So then I'll be left with this type of list. And then what I did is I put the 81 on. And that's where I got 81, 3, 24, 1511, and 42. Live lecture code hasn't updated. Oh, it should have. I've saved it. Has it updated now? I hope it's updated now. Because we are coming to the end of this lecture. I have fried everyone. I have stolen everyone's. I've mallocked all of your brain cells, and I have not freed them. I'm going to hold on to them a little bit longer, and I'll free them before the exam. So proud of that. No. Okay. So thank you everyone for tuning in. I hope that you are, I don't know, excited about what's coming next week, because it's no more new information. It's just going to be talking about the exam, and it's going to be, doing revision examples. We're going to go through many different examples. Hopefully, once you vote for me, I'll be able to see what everyone wants to do and then make up some questions to go with that. So hopefully that means you get a little bit more practice before the exam. I hope that you all have a good rest of the week. A really fantastic long weekend. I hope that you get to, do some of your assignment, but also you get to do something fun as well. And thank you so much for tuning in on this lovely Tuesday. I love all these puns. It's just fantastic. Maybe, think of some more for next week's lectures. But thank you for tuning in. I look forward to seeing you next week on a Tuesday. I know I spent 30 minutes today updating lecture slides because I thought it was Friday as well. And so did Tammy. We all thought it was Friday. It feels like a Friday. This week is done. Over and out. All right. Have fun, everyone. I'll see you all next week. Bye.